The paper discusses the use of a convolutional recurrent neural network, CRNN, to predict the evolution of spinodal decomposition in 3 dimensions, as described by the Cahn-Hilliard equation. A specialized, physics-inspired architecture is shown to provide close agreement between predicted evolutions and ground truth ones obtained via conventional integration schemes. The method can reproduce microstructures not represented in the training set at a fraction of the computational costs. Extremely long-time extrapolation capabilities are achieved, up to reaching the theoretically expected equilibrium state of the system, despite the training set containing only relatively short, initial phases of the evolution. Quantitative agreement with the decay rate of the free energy is also demonstrated up to late coarsening stages, providing an example of a data-driven, physically consistent, and high-accuracy machine learning method for long timescale simulation of materials. The CRNN model is trained on a dataset generated by solving the Cahn-Hilliard equation with a finite difference scheme on a cubic grid. The dataset is composed of 1850 sequences with different average concentrations and correlation lengths, split into a 70-to-30 ratio for training and validation sets. Each sequence is composed of 50 consecutive configurations separated by a time interval, allowing the NN to generalize to partially coarsened microstructures as initial conditions. The core architecture of the CRNN is based on a previous work but with 3 critical modifications: 3-dimensional convolutional layers, a deeper mapping between the input, hidden, and output layers in the recurrent modules, and a new output layer inspired by the physical formulation of the underlying problem. This physics-inspired layer ensures the exact conservation of concentration by construction, making it suitable for other diffusive processes. The resulting NN model contains approximately 2.9 times 10 to the 4 parameters and is trained using a mean-squared error loss function and the atom optimizer. The paper demonstrates the generalization capabilities of the CRNN, both in terms of computational cell size and length of the generated sequence. Predicted sequences are shown to reach the correct stationary state of the system, despite the CRNN only being presented short, far from equilibrium sequences during training. Quantitative comparison between predictions and ground truth evolution is performed, both in terms of local, voxel-level correspondence and global thermodynamic properties. Statistical significance is also tested. The paper presents a novel approach to solving the Cahn-Hilliard equation using a convolutional recurrent neural network, CRNN. The CRNN is trained on a dataset of phase field evolutions generated by finite difference methods and learns to predict the next state in the sequence given the previous one. The architecture of the CRNN consists of a series of convolutional layers followed by a recurrent layer and a specialized, to flux, layer that converts the hidden state to a vector field. The model is trained using the atom optimizer with a learning rate of 10 to the power of 5 and a mean-squared error loss function. Data augmentation techniques such as reflections, rotations, and Z2 symmetry are also employed. The results show that the CRNN can accurately predict the phase field evolution even when tested on larger computational domains and longer sequences than those used in training. In particular, the model demonstrates good generalization capabilities in terms of domain size and evolution time, as well as its ability to handle qualitatively different initial configurations. The authors also test the model's ability to generate long sequences by iteratively feeding the predicted output back into the network, finding that the model maintains a close correspondence with the ground truth evolution despite local variations. Overall, the paper demonstrates the potential of using CRNNs to solve complex partial differential equations like the Cahn-Hilliard equation, offering a promising alternative to traditional numerical methods. The approach could be particularly useful for problems where the underlying physics is well understood but the computational cost of traditional methods is prohibitively high. The paper discusses the application of a deep learning model, specifically a convolutional recurrent neural network, CRNN, to simulate the Cahn-Hilliard equation. This equation is a fundamental model in materials science that describes the dynamics of phase separation and coarsening in binary systems. The CRNN model is trained on a dataset of spinodal decomposition simulations, with the goal of predicting the microstructure evolution over time. The authors demonstrate that the CRNN model can accurately predict the long-term behavior of the system, including the formation of a layered microstructure, which is one of the expected stationary solutions of the Cahn-Hilliard equation under periodic boundary conditions. They also perform a quantitative analysis of the predictive performances, using metrics such as the root mean squared error, RMSE, and the average local distance between the predicted and true interface, delta. The results show that the CRNN model can learn the underlying physical mechanisms of the Cahn-Hilliard flow and predict the microstructure evolution with high accuracy, even for sequences much longer than those provided in the training set. This demonstrates the generalization capabilities of the CRNN model and its potential for simulating complex physical systems. The paper discusses the use of convolutional recurrent neural networks, CRNNs, to predict the microstructural evolution of materials undergoing spinodal decomposition in 3 dimensions. The authors show that CRNNs provide an excellent approach to approximate the microstructural evolution at a fraction of the computational costs of the explicit method used to build the training set. Close correspondence for evolutions much longer than those provided in training has been demonstrated. The CRNN is found to properly predict the stationary states consistent with the learned equation, despite never being observed at train time. The authors also address the problem of the wrong exponent in the free energy dissipation observed at the end of the evolution in Fig. 6a. By exploiting the low cost of machine learning predictions, they report in logarithmic scale the average free energy decay curve over 10 independent evolutions 80,000 tau long on a 128 x 128 x 128 grid, each starting from a different Perlin noise initial condition. One standard deviation interval is also reported with the red shaded area. As it can be clearly appreciated, the average long-time behavior exhibits the expected t-1/3 power law, showing that the acceleration previously reported is not systematic. The paper concludes that the use of fully convolutional and recurrent structures, together with a physics-inspired specialized layer, yields the accurate generation of spatiotemporal sequences at a fraction of the computational costs of the explicit method used to build the training set. Close correspondence for evolutions much longer than those provided in training has been demonstrated. Notably, the CRNN is found to properly predict the stationary states consistent with the learned equation, despite never being observed at train time. This research paper focuses on the development of a machine learning-based model for predicting the evolution of spinodal decomposition in a binary polymer mixture. The model utilizes a convolutional neural network, CNN, to simulate the phase field of the mixture, which is crucial for understanding the microstructure evolution in materials science. The authors demonstrate that their CNN model can predict the spinodal decomposition process with high accuracy, outperforming traditional pseudospectral methods in terms of computational efficiency. The paper begins by introducing the concept of spinodal decomposition and its importance in materials science. It then discusses the phase field method, a mathematical model used to simulate the microstructure evolution during spinodal decomposition. The authors explain how they developed their CNN model, which takes advantage of the spatial and temporal correlations inherent in the phase field data. The authors also discuss the challenges of training the CNN model, including the need for large datasets and the difficulty of ensuring that the model generalizes well to new, unseen data. They describe their approach to addressing these challenges, which involves using a combination of real and synthetic data for training, as well as techniques such as data augmentation and transfer learning. The paper presents several experiments that demonstrate the effectiveness of the CNN model. In these experiments, the authors compare the predictions made by the CNN model with those obtained using a traditional pseudospectral method. They show that the CNN model is not only more computationally efficient than the pseudospectral method but also produces more accurate results, particularly at later stages of the spinodal decomposition process. In addition to the main text, the paper includes several appendices that provide further details on various aspects of the research. For example, Appendix A discusses the computational costs associated with the CNN method, while Appendix B examines the effect of mesh rescaling on the evaluation of the root mean squared error, RMSE. Overall, this paper presents a significant advancement in the field of materials science, demonstrating the potential of machine learning techniques to improve our understanding of complex physical processes.